The act of sorting things can be tedious, but sometimes we have to. Maybe you have to sort some documents, or maybe you work at a library and you have to sort books, or maybe you're making a top 10 of your favorite movies and sorting them from 1 to 10, or maybe you have to do a computer science assignment. This doesn't change how tedious and time consuming it can be to sort things, and it can get worse. Imagine having to sort hundreds of items, or thousands of them. Thankfully, we now have computers to do this. But how do the computers do this? Well, they use sorting algorithms, and thus the hard work of sorting things can be placed onto the computer. There are many sorting algorithms out there. Let's look at one of them, called BeadSort, or gravity sort. BeadSort, or gravity sort, uses the power of gravity to sort numbers. It is best to look at BeadSort by visualizing an abacus. You know, that thing. For the sake of example, let's sort a bunch of random numbers. In this case, 5, 1, 4, and 3. First, we need to find the largest number. In this case, that is 5. Then, we need to look at how many numbers we are sorting. We are sorting 4 numbers. When we visualize our abacus, we need 5 lines and enough space to fit 4 beads on each line. So here is our simplified abacus with 5 lines. And we can easily fit 4 beads on each line. Let's represent beads using coins. So first of all, we have 5 beads in this row, representative of the number 5. Then we have 1 bead representative of 1, and then 4 beads representative of 4, and then 3 beads representative of the number 3. Now, what happens when we introduce gravity? Well, naturally, the coins will start to fall. And now, if we count the amount of coins in each row, we can look and we can see a sorted list. We have 1, then we have 3, then we have 4, and then we have 5. And now our numbers have been sorted.
The bead sort is expressed in 4 varying levels of complexity. The first level of complexity is when all the beads are moved at the exact same time. This would be a simple physical example like the abacus. The second level of complexity would be in a real physical model where gravity is taken into account. The time it takes for the beads to fall is proportional to that of the square root of the maximum height, which is proportional to n. The third level is when beads are moved one row at a time. This is the case used in the analog and digital hardware solutions. The fourth level is when the bead is moved individually. It checks if there's an empty space below a bead and drops it one level if there is so. This is used for software implementations of a bead sort.
This is how it would work in theory. However, to do this in code, there are different ways to implement this. Recall our abacus from before. Each coin can instead detect if there's an empty space below it. There's an empty space below this coin, thus it'll move. There's an empty space below this coin, thus it'll move. Thus this one will move, this will move, this will move. And now we have our sorted list. 1, 3, 4, and 5. However, this isn't the only way to do it. Instead of placing the coins where the numbers gave it to us in 5, 1, 4, and 3, we can instead place the coins onto the abacus where they would end up. So, recall our numbers. 5, 1, 4, and 3. First, we can place 5 coins at the bottom this time because that's where those coins would end up. Then, we can place 1 coin. Then we can place 4. And then we can place 3. As you can see, once again, we have our sorted list. 1, 3, 4, and 5. Now let's show it to you in actual code.
Here, we have made a sample program that uses the concept of bead sorting to organize a group of 10 numbers. This section of the program initializes a 2D array and prints it to represent the 10 numbers into an abacus. In order to use the bead sorting method, we need to find out the highest number in the group. In this case, we have made a simple for loop that compares each of the 10 numbers with one another and sets the higher number as the max. The next thing we did was make and initialize a 2D array for the numbers. Each row represents a number, and the number of columns represents how much the number is worth. We also initialize an array called count in order to track how many beads are there per row. The next thing we do is drop the beads. First, we make a for loop to repeat this process for all the numbers. Then, we set a temporary integer to store the current number in order to keep track of how many beads we've dropped. Next, we make another for loop that runs as long as the temporary integer is greater than 0. This for loop subtracts 1 from the temporary integer to represent that we've dropped a bead. Then, we update our grid such that the count increases by 1 after each bead drop and sets the new location of the bead dropped as a $sign. The count array allows us to stack beads on top of each other without overlapping. Next, we print our abacus to show the newly sorted array. Finally, the last step is to count the number of beads. We do this by making a counter and running through each row of beads. We add onto the counter until the program sees something that isn't a $sign. The method then returns the sorted array. The output of our program looks like this.
So why would you use BeadSort? Well, for most applications, BeadSort is a terrible sorting algorithm and only works as a novelty. Essentially, it only looks cool. BeadSort is terrible because 1, it only works for positive integers, and 2, it takes up a lot of space in a program. In our demonstration, we sorted relatively small numbers. The biggest number was 5, so we needed 5 lines. But what happens when the biggest number is 10? Well, we would need 10 lines. And what happens if the biggest number is 20? Well, we would need 20 lines. In a program, this would represent the amount of columns in a 2D array. And as we sort more and more numbers, the 2D array must have more and more rows. The biggest number is equal to the number of columns, and the amount of numbers is equal to the amount of rows. If we have super big numbers to sort, like 1,000,000, we would need an array that has 1,000,000 columns. This makes BeadSort super space inefficient, and is the record holder when it comes to wasted space.